So next we wish to show that N is not only a subspace but a closed subspace. And to do that we're going to let the set Fn be a Cauchy sequence of vectors in N with Fn being defined as such. So before we continue, we want to make a quick statement that if I let F be an element of N, then the norm of F squared is equal to the norm of a sum alpha in A, lambda alpha, E alpha, for some set of complex numbers, lambda alpha, norm squared. But using theorem 3.25, if alphas converge, then I can pass the norm through the sum if it's squared. So this is going to be equal to the sum alpha in A of the norm lambda alpha E alpha squared. But this is just going to be, as discussed before, the sum alpha in A of the norm lambda alpha squared. Yes? So, moving forward, if I consider for any alpha in A, if I pick one such alpha in A, we get that the norm, it's a complex number, so the norm of lambda alpha n minus lambda alpha m is less than or equal to the sum alpha in A of the norm and alpha minus lambda m alpha squared. And the reason for this inequality is simply that this here is one of the terms inside of this sum. But this is now equal to Fn minus Fm. And this follows from what we showed up here. So, because of this, we get that because the Fn's are Cauchy, we get that for any given alpha, the lambda alphas are Cauchy. So hence, we get lambda alpha is equal to the limit as n goes off to infinity of lambda alpha n exists. Now, knowing that, we can say for any f in our curly f, which again is the set of all finite subsets of A, we have the sum alpha in f of our newly found to exist lambda alpha squared is equal to the limit as n goes off to infinity of the sum alpha in f of the norm and alpha squared, which is less than or equal to the limit as n goes off to infinity of the sum alpha in A, again we define A using a limit of the f, so this is always going to be less than or equal to that one, of the norm alpha A n squared, but this is equal to the limit as n goes off to infinity of the norm of Fn squared, which we know to be finite because we know that Fn is Cauchy. So, from this, hence, we get that f is equal to sum alpha and a lambda alpha e alpha is a well-defined element of n. And this, again, follows from the fact that we have showed that this here, the sum for each f of our newly found lambda sub alphas, is bounded by the norm of the f sub n's squared, which is finite, and hence this is finite, which means that this sum here is well defined, again by theorem 3.25.